All right. So today we're going to talk about force and weight. Um, Let me move my face over here somewhere. So what we want to do is we're going to try to solve problems similar to this one. Weight and force are connected because gravity is a force that pulls everything down towards the center of the earth, and we measure that. So when we measure your weight, we're not really measuring your mass per se. We're actually measuring how much force Earth is pulling down on you. And the relationship between that force is, well, there's a formula, and I'll cover it eventually with you guys. But basically, it has to do with your mass times the mass of the Earth divided by the distance between you and the mass squared, or you and the Earth squared. So, um, anyways, we got to be very careful in a physics class when we talk about weight and mass. They're not the same technically, okay? So just keep that in mind. Write this down. This is important. Okay. So when we talk about the force of gravity, there's a couple of different formulas that you could use. The easiest one is the gravitational force on your body is, and I want to write this down so you guys, so it doesn't get lost. Um, and I can't remember if we've covered this part in class or not, but um, let's write it down just to be safe. So, whoops. There it is. Force is equal to the mass times the acceleration. Okay, that's one of Newton's laws that we'll talk about later. And so g is the acceleration due to gravity. All right, it's 9.8. So when we did the t-shirt drop, if you did all of your math right, collected your data, and used the formulas correctly, you got an acceleration pretty close to 10. It should have been 9.8 in a perfect world, right? So if we dropped those t-shirts in a vacuum and air wasn't an issue and we had the most precise equipment, it would be perfectly 9.8. And that's at sea level. If you go higher up in the mountains, that would change, right? So that's at Earth's surface. Okay. Um, and so that number of 9.8, that keeps coming up over and over and over again. And the reason this relates to the T-shirt launcher project is, well, the T-shirt has a mass. It's going to be accelerated down towards the ground at a rate of 9.8 meters per second squared. And sometimes in your homework, you'll also see this written as, and they're the same really. You'll see this written as 9.8 meters per second squared. Okay. All right. Does everybody have everything written down? I move on to the next slide? All right. So Sir Isaac Newton was the first person to explain why objects move the way they move with regards to free fall. Remember, the story is that an apple fell from a tree. He was sitting under the tree. The apple hit him in the head, and he goes, "Huh, I wonder what causes this apple to fall on my head." And then from there, he, out of just curiosity, he started dropping things and measuring things. Now, he wasn't the first one to do it. Galileo was probably the first person that recorded it and did it in kind of a scientific method approach. So Isaac Newton kind of piggybacked on that and just started doing it, measuring it, and then he came up with his laws of motions. But his laws of motion basically focus on two things: the mass of the object and the force of the object. Okay? So the majority of this class, we talk about mass and force. Okay? And he did this a very long time ago. So he was alive from 1642 to 1727. So that's, what, 300 years ago is when he passed away. And when you think about that, these equations that we use today, like SpaceX used to kind of rescue those astronauts, that was in the news last week. It's the same equations that this guy came up with 300 years ago. Yeah. And think about it's just out of curiosity. Something fell down. He goes, what goes up must come down. Why does it come down? How does it come down? Is there a pattern in which it comes down? What are those patterns? Can I predict the way that it comes down? And when he was doing his work, he noticed that the math, which was just algebra, didn't seem to cut it. So some say he invented calculus to do his physics work. Others argue that there was another guy named Leibniz who was inventing calculus at the same time. So that people will say one invented it, the other one. It doesn't really matter. He applied it to physics. So if you take a calculus class, you could thank this guy for that too. Very smart person. But really just curious. All right. So all matter, you don't have to write this down. You just have to kind of read the screen and kind of go along with me. All matter has a mass and it takes up space. A solid rock has mass. So do gases and liquids. They have a mass. So the air in this room has a mass. That's why it's called air pressure. The air molecules are bouncing off the walls. They have a mass. They take up space. There's probably millions, if not billions, of air molecules in this classroom right now. And they're just bouncing against our skin, and we're just kind of used to it. With your hand out the window when the car's moving, you can feel the mass of the air pushing against your hand. Has anybody ever done that? Where you roll down your window and you just kind of do this with your hand? Well, what's hitting your hand is air. It has a mass. You feel it, right? Everybody's curious about my little weights that I have here. Oh, see this? This little weight. Okay. Well, the SI unit for mass is kilograms. So when you see an object like this, this is 2 kilogram mass. I have a little, I don't know if you guys can read that or not, but I have a little weight right here. It's funny, we call them weights, but really they're masses. This one is 300 grams, so it's a tinier one. I have another mass right here. This one's pretty big. This one is 1 kilogram. See? 1,000 grams, 1,000 lowercase g grams. So don't get those two confused, because sometimes, let me write that down in the notes here. So this would be 2 kg. And don't get confused, because sometimes G means grams as a unit of measure. Oops. Be sure to write this down. And then sometimes G means 9.8 meters per second squared. That's the acceleration due to gravity. Okay. Does everybody have that written down? Okay, I can wait. Okay. Now? Okay. All right. So what is force then? Well, force is a push or a pull. Make sure you write down push or pull. And I'm just going to turn this off. I'm tired of moving that around. Forces can cause an object to change its motion. Can you give some examples of forces? Yeah, somebody pushing or pulling. Anything that involves pushing or pulling, right? Lawnmower, I push the lawnmower. Kid in a wagon, I pull the wagon. I'm applying a force. There are natural forces too, like waves, right? There's a whole big thing of renewable energy, and when the waves come to the shore, they push. They also pull when they go back, right? And so they have generators that generate electricity based on these pushes and pulls. I don't know if anybody's ever been to Hoover Dam, but it's a pretty big thing, and it just lets the water. It's formed a lake on one side, but on the other side it's just a river. So the dam actually lets the water pass through, and as it passes through, it turns turbines. Those turbines generate. They're connected to a generator, and it generates a lot of electricity. Okay, push or pull. Our t-shirt launcher, we're going to push the t-shirt out of the launcher, and gravity's going to pull it back down. And where it lands is based on these laws of motion. Okay. So weight is a push or pull. That's the earth pulling on us. Friction is a force. It fights against the natural. If you take your hands and push them against the table, you'll feel the table push back. That's a frictional force. Tension on a rope, right? And we'll talk more about that. The force of a spring. If I take a spring and I stretch it out, that spring's going to want to go back to its regular size. Or if I compress a spring. Some springs you can press. If I push the spring like this, as soon as I let go, it's going to want to go back to its regular state. And then there's another thing called electrical force. It's actually electromagnetic, right? Electricity and magnetism are kind of the same. They're connected. I don't know how to word it. In simple terms, I don't want to be all physicsy on you guys. Our first day back from spring break, but yeah, there's a force for sure, and it has to do with charges, right? So if you take a balloon and you rub it on your head, it sticks to the wall. That's a pull. There's an attractive force at work. Okay, and that's an electric force. Static electricity. But anything where you push or pull, that's a force being applied. And it does have an impact on motion. So think of anything like anything in that list or anything that involves a push or a pull. It changes the direction that an object moves. So think of the apple falling on Isaac Newton's head. The apple was stationary, sitting in the tree, just minding its own business. And when it was ripe enough, the tree was like, all right, I'm going to let you loose, because the apple has seeds, and that's how the trees reproduce. That's how you get more trees. Sometimes little critters come along and eat the fruit, and then wherever their bio waste goes, it kind of plants the seed. That's really the intention. That's how nature works. But as soon as it's released, it falls to the ground. That's gravity pulling it down. So you do want to write this down. Quantitative and qualitative are two things that we talk about in science a lot. Quantitative is when you measure or calculate things. Quantitative is a number where you can do math with it. If you live in 1234 Main Street, that's a number, but it's not quantitative. I'm not measuring your address. In a sense, I am, but it's not the same. Okay. So force is measured in newtons. Since the guy created it, I guess he can call it that. 1 newton of force is equal to the change in velocity of 1 kilogram object by 1 meter per second per 1 second. So let me expand on that. Remember that force is equal to the mass times the acceleration. So what they're saying is that if you have a mass of 1 kilogram times the acceleration, which is 1 meter per second in 1 second, which is 1 meter per second squared. 1 times 1 is 1, and it's technically kilogram meters per second squared, or 1 newton. Okay? So when you think of a push or a pull, you're going to push or pull something that has a mass, right? In the t-shirt launcher, the Earth is pulling the t-shirt. The t-shirt has a mass. It's going to pull it. The acceleration due to gravity, though, is going to be 9.8 meters per second, which, by the way, is the weight of the t-shirt, right? The mass times the acceleration due to gravity. So the weight of the t-shirt does come into play, sort of. Sometimes it does, sometimes it doesn't. So the interesting thing about the acceleration due to gravity is that it's the same for anything, no matter how massive an object is. It always speeds up at 9.8 meters per second squared. All right, can I move on to the next slide? All right, let's write this down. Weight is a force of gravity acting on objects with mass. How is weight different than mass? So when you sit on a scale, or stand on a scale, I should say, it's actually measuring how much the earth is pulling on your body, on the mass of your body. It's not really your mass. Now, what's really interesting here in the United States, everything's done in pounds. The rest of the world, in fact, so it's called the imperial system because it's the British system. Ironically, the British system uses the metric system now, which is kind of funny. In most things, some things they don't, but it's kind of funny. The rest of the world uses the metric system. So remember, and write this down, we said that the force is due to the mass of the object times the acceleration. But when we say the force due to gravity is the mass of the object times g, and that's the g where we say g is equal to 9.8 meters per second squared. This is also, you'll see some textbooks call it the weight. So the weight is about 10 times more than the mass, right? So you could say that your weight is 9.8 times the mass of the object. And let's label that too, that's mass. You don't need to write this down, just pay attention. Mass is intrinsic property that measures the quantity of matter in an object. Your mass does not change if you go into space. Okay? Your mass doesn't change. You don't change how much stuff your body is, right? It just doesn't change. Your mass doesn't change if you go out into space. Now, weight is an extrinsic property that depends on gravitational force. Your weight will definitely change. So remember the astronauts that they just rescued from the space station? They said that they went through some health issues. Some of them are taller, right? They got taller because gravity isn't pulling their bodies down. So when we walk around, and as you get older, I'm a little shorter than I was when I was in my 20s. Gravity pulls you down, it compresses, right? Well, when you don't have that in space, now your mass is the same. Actually, they lost a little weight, but that's just because, the food, there's not, you're not able to eat Krispy Kreme donuts in space, stuff like that. But they were just taller and thinner. They were just kind of stretched out a little bit. But they weighed zero, or pretty close to zero. So in outer space, you basically don't have, it's very little weight because you're so far away, Earth can't really pull you down, right? It does a little bit, but it's not even close. Here's a fun fact. On the moon, you would actually weigh 1/6 that of what you would weigh on Earth, because the moon is about 1/6 the mass of the Earth. So because it's a smaller object, smaller planet, sort of, not really a planet, but it's a moon, but it's a smaller mass. It's about 6 times smaller than the Earth. Gravity on the moon is 1/6 of the gravity here on Earth. I do want you to write this stuff down. Mass is a scalar quantity. Remember that vectors have a direction. Weight is a vector because it has a magnitude and a direction. The direction is always towards the center of the Earth. So if you're on a hill and you're kind of at an angle, it doesn't matter what that angle is. Your mass is going to be pulled down towards the center of the Earth. Okay? And you'll hear me say that a lot. We're going to start doing some calculations. I don't know if we'll get to them today or not. It really depends. But we're going to do some calculations, and I'll say, remember that the acceleration due to gravity is going towards the center of the Earth. Gravity pulls you towards the center of the Earth. So scalar is a quantity. 60 kilograms is just a quantity, right? If you have something that has a mass of 60 kilograms, that's not really a weight. But if I say 60 newtons or 600 newtons, and I say the weight is 600 newtons, I'm literally saying that Earth is pulling on this object with a force of 600 newtons towards the center of the Earth, so it has a direction. So vectors always have a direction. All right, can I move on to the next slide? All right, so we already wrote this down. You don't need to write it again, but let's just say it again so it kind of sticks in your brain. The force of weight, or weight is the force of gravity acting on an object, is really the mass of the object times g, and g is equal to 9.8 meters per second. So sometimes they write it like this, but sometimes it's written as 9.8. It means the same thing, meters per second squared. Okay. So let's do this. 1 kilogram of water weighs 9.8 newtons. Okay, so I just write that down real quick because you're going to do some homework at some point, maybe today, maybe next time. Probably today, though. I think we could probably do some of these simple problems today. again, the weight of an object is equal to the mass times g. In this particular case, the mass was 1 kilogram. G is always going to be 9.8 meters per second. Always. Always. And so when you do the math, you get 1 times 9.8, which is just 9.8 newtons. One thing they do, we wrote this down in our notes before, but they said that's 1 liter of water. So you might want to write this down. 1 liter of H2O equals 1 kilogram of mass. That's how they define a kilogram. Actually, they say 1 cubic centimeter, which weighs 1 gram. And so then if you ramp up to a liter, then 1 liter weighs 1 kilogram. Or has a mass of 1 kilogram. It weighs 9.8 newtons. See, even I have a hard time keeping the two to track. Or, I don't know, I'm tired. All right, can I move on? So because it's a vector, though, it has a direction going towards the center of the Earth. So we did a bunch of math. We have to remember that the force is a vector, and it's going straight down. So when we go to do the math on a lot of the stuff, we're gonna have to basically calculate where the t-shirt's going to land and how it's going to land. We're going to track a lot of vectors, and the easiest way to track the vectors is to draw the arrows. And we'll talk about that next time, about a free body diagram, so you could keep track of where all the arrows go. Okay? We are almost done. Well, if you go to the moon, the acceleration due to gravity is 1/6 that. So write this down. So the acceleration due to gravity on the moon is only 1.62. While on Earth, it is 9.8. So it weighs 6 times less. They're pretty close to 6. Okay, can I move on? So in English, unit for force, which we'll use on Earth, is pounds. And so I want you to write this down. 1 pound is equal to 4.48 newtons. It's a measurement of force, not mass. 1 newton is equal to 0.225 pounds. which is funny. When you go to the weight room, guess what? They're not exactly right. They'll tell you the measurement of the weight in pounds, and then they give you the weight in kilograms. But kilograms is a measurement of mass, not weight. Interesting. So if a person weighs 125 pounds, what is her mass in kilograms? Well, that's how much she would weigh in newtons, right? So we convert the 125 pounds, because there's 4.48 newtons, 4.448, forgot a 4, newtons in 1 pound. So that converts it to 556 newtons. And then we do a little algebra. Basically, we divide that by the 9.8 Newton kilograms, and you get 56.7 kilograms, right? And that's what I said it was, right? Just by looking at the scale, I was like, well, it's probably 57 kilograms, so that's a pretty good guess. Which is interesting because the scale measures pounds, which is a weight, but then when it converts it to kilograms, it's a mass. I don't know if you guys are picking up on that. So the conversions are right. It's just one is a measurement of weight and the other is a measurement of mass. And it's the same thing for the weights at the gym. If you're lifting pounds and you know it's whatever 220 pounds, that's probably 100 kilograms or close to it. So there's that. Did everybody have that written down? Can I move on to the next slide? We are almost done. So I don't know if you picked up on this, but if you take this and divide by m and divide by, or not m, divide by g. If you take that original equation and you divide it by g on both sides, you'll get this. M is equal to the force or weight divided by g. And remember that g is equal to 9.8 meters per second squared. And then sometimes it's 9.8 newtons per kilogram. Those are the same thing, by the way. Okay, so just a little algebra. All right. Real quick, you don't have to write this down, but if you take a trip from the Earth to the Moon, which statement below is correct? Your mass and weight both have decreased. Your mass stays the same, but your weight decreases. Your mass decreases and your weight stays the same. Your mass increases and your weight decreases. So which one do you think it is? Which one? Think it's C? Anybody else think anything else? You say B? You are correct. It's B. Your mass stays the same, your weight decreases. Because the acceleration due to gravity changes. Okay?
I'm so smart. I wasn't even paying attention.
Whoa, relax. You did a good job. Calm down.
Hey, man.
All right. So what is the weight of this dumbbell? All right. So I have a force, right? So when I this is a force, 50 newtons, and then a 10 kilogram is resting on the table. So this is a mass. So it says, what is the weight of this dumbbell? Well, if the spring has to pull it at 50 newtons, right? We also have to remember that gravity is pulling it down. So it doesn't matter what the spring is doing. We can find the weight by just figuring out, well, what's the mass of this thing? Well, this is the mass. And what's the acceleration due to gravity? Remember that G is equal to the mass, not mass, is equal to 9.8 meters per second. So that's the first part. So it's being pulled down this way, but this is being pulled up this way. So let's do this one real quick. What's the weight in newtons? Well, we just have to do the conversion. And what's the person's mass? Divide by G. So I'll just leave that up there. And this is the last slide for our notes. So write those down.